The Antarctic is the coldest place in the world.
Exactly.
Yeah. So minus 90 degrees has been recorded in the middle of the Antarctic. But where I go, it's not as cold as that because I'm right on the edge. So I'm on the marine side. It's a bit below zero where I go most of the time, but then it can go above zero.
Fantastic. Well, I'm here with Lloyd Peck in his office at the British Antarctic Survey. And Lloyd's just been to the coldest place in the world, as you were just saying. It's a gorgeous spring week here in the UK. Blackthorn Blossom Week has come out. And you've been in the cold south. And so you've been going back and forth as a lead polar scientist here at the British Antarctic Survey for 21 seasons.
Yep, my 21st season this time around.
Fantastic. Well, it's fantastic with that experience, but we'll hear a bit about the changes that have been happening over that period of time. So you're based at the Rothera Research Station in Antarctica. Tell us a bit about life there. I mean, we were conversing by email, so now you've got kind of contact. You can contact people in real time almost around the world, which is lovely. So you've got some kind of contact. But tell us paint a picture of life at Rothera Research Station in Antarctica.
So let's make it a contrast, because you mentioned spring and the blackthorn. So I've just come back from 2 months in the Antarctic, and there's a big blackthorn copse just on the footpath south of here, and there's an arch over the footpath. So you get this white arch which sheds petals as you go through the season. But also, I haven't seen trees, I haven't seen grass, I haven't seen any flowering plants for 2 months, and I've come back and there are daffodils, narcissus, crocuses, the whole lot, and I've only been there for 2 months, but that's blown me away as the difference between that and what we've got in the Antarctic, which is rock and ice. There are seals there, there are whales there, there are penguins there. There are plants, but they're mosses and lichens and the odd, very small grass plant. So the contrast between there and here is extreme. Yes, I've been going 21 years. I've seen massive changes. We live on a station that is designed for about 100 people and currently has about 150 there because it's going through a massive building program. And 5 buildings that I'd spent 2 decades working in and out of have now gone. And we've replaced
it.
They've been replaced by one big central building, the new Discovery building, and the facilities in the new Discovery building are really good. They're better than we've had before. But I have a history with the old buildings, and I felt kind of an emotional tie to them, and watching them go has been a bit of a struggle for me this year.
I suppose that's sending a signal that research in the Antarctic is even more important. That amount of resources going in, supported by research councils in the UK and the British government, sending you down there as British Antarctic Survey. So how have things changed over those 21 years? I mean, we would expect there to be changes due to climate. Paint a little bit of a picture for that as well.
So there have been changes everywhere. So when I first went to the Antarctic, our communication with the outside was via telex, and you got 100 words on a telex machine a week. And
you had to put stop at the end of sentences.
And you had to put stop at the end of each of the sentences, and everything that I sent back to my wife was typed into a telex machine by the telex operator. So everybody on station knew everything that was going backwards and forwards.
No secrets, you know.
And now we've got electronic communication. We've got the ability to have WhatsApp. We have emails going backwards and forwards. We can have meetings through Teams and Zoom, and that has benefits and negatives. So the benefits are you can be in touch with your loved ones and your friends in a way that you just couldn't possibly 20 years ago, 30 years ago. But also I can now be expected to be in meetings during the day while I'm doing field work in the Antarctic, and I almost resent that because I find that an intrusion. And the access for other people to get to you is way higher. So I now spend my days doing field work and my evenings doing my job back here. Whereas I used to spend my days doing field work and my evenings analysing data and trying to work out what was happening.
Being immersed in it all. I mean, that's field work, isn't it? That's kind of like. But now the rest of the world's intruding a little bit.
Now the rest
I
of the world.
hadn't thought of that.
And you're not just doing field work, and as you say, immersed in the field work. You're now immersed in the field work for part of the day, and then you're doing the other things later on. The world has changed in the Antarctic where I go. So the station that I go to at Rothera has a very big glacier about 10 kilometres away, and in the time I have been going south, that glacier is receded 2 miles. So I can now go and sit in a small boat where all the way around me for at least a mile in each direction there would have been 500 feet of ice, and it's not there anymore. And just across the point from where the station is, there's a glacier that people go to skiing fields at the top, and that has receded between 50 and 100 meters since the last time I went to the Antarctic 2 years ago. And an area of rock the size of a very big detached house or a small block of flats has come out of that glacier, and we think it's been at least 1,000 years since that rock last saw the light of day. It has shells from limpets on it. So when gulls eat limpets, they eat the whole limpet, they digest the soft tissues, and they spit the shells out. And they regularly go to the same place to spit them out, and you get middens of limpet shells. And in some places they can be many meters deep. And on these rocks we've got a good sprinkling of those shells. So we're going to have them carbon dated, and we're going to look to see if their sizes and their growth rates were different from today's.
Wow. So it's rather like the middens in ancient cities, in civilizations, humans throwing away their waste in the same place and building up, and you're doing a kind of archaeological piece of work almost by finding out the different layers and different times.
Absolutely. So that they are the trash that the gulls spit out after they've eaten a meal, and they build up over time. And you can look back, and by looking at things like the isotopes in the shells, you can tell things like what the temperature was when they were laid down, because you can look at ratios of carbon isotopes and oxygen isotopes, and that tells you things about the temperature in the local environment. So you can use those data for a lot of things. We also had no sea ice in the last winter, and it's the first season I've ever known where there was no sea ice at Rothera, and there were humpback whales swimming past the point at the station all through the winter. My first 8 or 10 seasons there, we were driving skidoos over 1 metre thick sea ice to the nearby islands for most of the winter, and for 1 or 2 of those seasons up till Christmas. And the idea that none of that ice has built up this year, I find really worrying. And the rate of melt is higher in the last 2 or 3 years than I've ever seen there. And I find that, you said how do you feel about going south, I find that really hard to take now, because I can see it accelerating, and I can see us not getting to grips with the problem in the way that 20 years ago, when I gave lectures on television about climate change in the Antarctic, I hoped that by now we would have had some traction on that, and we would have slowed things down, and we haven't. It's still accelerating.
And once you know that, next time you plan to go, you'll be thinking it's going to be, I'm expecting to see dramatic changes again. That suddenly becomes a norm rather than an unusual thing. And that's going to have, for all of us, some kind of psychological impact as well on what we see. Now you're a biologist, so your kind of expertise is in the biology of cold waters, of super cold waters. So tell us a little bit. I mean, you dive in the Antarctic, so it's not all by remote submersibles; it's by remote submersible people. And you go down. So tell us a little bit about that. Dramatic pictures of you coming out of the ice, having icy water, should I say, having dived in it. Tell us a bit about the kind of biology that you've been studying in the super cold waters of the Antarctic.
So most people think, and they're taught this at school and university, that very little lives in the polar regions. And on land, that's probably true, because if you go from tropical rainforests, there's almost a kind of monotonic decrease in the amount of life as you go towards the poles. In the sea, that's just not true. So on the seabed where I work in the Antarctic, there are 20,000 species of animals living on the seabed. And okay, we think there are about 30,000 in Europe and about 25,000 in South America, but 20,000 is not far off that. So
it's a big number, isn't it? I mean, already.
It's a big number. And life is abundant, it's very diverse, and it's very different from life elsewhere. So the species that I look at are cold-blooded. Their body is the same temperature as the environment. And that means that certainly in the high Antarctic, those animals live with their bodies at temperatures below zero or around zero all the time, all the way through their lives. And that means there are lots of consequences for that. Everything runs slow because, as we know from school, if you want a chemical reaction to go faster, you put heat underneath it and you warm it up and it goes faster. So those animals then have all their chemical reactions in their cells going slow. And that means they grow much slower than you would expect animals to grow here. And the biggest effect is probably on development of embryos. And I've worked a lot on the development of embryos because it's one of the sort of, I think, most astonishing effects of temperature. And when you get close to 0 degrees, the development rates of animals go down even faster than you would predict from the low temperature. And something else is happening here. And I think it's to do with things like the viscosity of the fluids inside the cells getting really sticky, which means it becomes even harder and harder to do things like make proteins. So the classic example is, I've looked at the rates of development of embryos of snails that live in the sea. And they're easy to measure. You don't have to be a great scientist to do this because lots of these snails lay broods on rocks. So you just watch for when they lay a brood on a rock. And then you just watch the brood until the little juvenile snails crawl out. And that's the time it takes to go from a fertilised egg to a juvenile snail. Now in the tropics, that can be as short as a day. It's often 2 to 3 days. It's never more than about 4 or 5 days. Around the UK, it's usually about 2 to 3 weeks. And when you get up to the colder temperatures of Norway, it can be 20 weeks or 30 weeks. Where I am in the Antarctic, it's between 60 weeks and 2 years. And if you go to the highest parts of the Antarctic, where it's permanently below about minus 0.5, and sometimes it stays around about -1 to -2, it takes 8 years to 10 years.
So when you say highest part of the Antarctic, you don't mean high above, you mean
highest
latitude. So
yeah.
furthest towards where the South Pole is.
The coldest seas, so where the temperatures in the sea
so it could be
never
come 2 years.
2 years where I go, and the temperatures go from -2 to about +1. And then when you go that little bit further, so the temperatures don't come above 0, 8 to 10 years. And so that shows the massive effect that even a very small temperature change has. And that, I think, has something to do with the change in the physics within the cells.
So they've got a kind of antifreeze in them, some sort of like ethylene glycol or something. So, much more complex than that, but there's something that's stopping them freezing, isn't there?
So 2 things can happen. One is, in fish, they have to have antifreeze because fish blood is less concentrated than seawater. So they would freeze at about -0.5, and every fish in the Antarctic experiences, certainly in the shallow waters in the Antarctic, experience temperatures below that every year. So all the fish have a range of antifreezes. The first one discovered was a thing called a glycoprotein, a mix between a protein and a sugar. And that takes the freezing point of their bodies down to about -2.5 to -3. But you also, in the invertebrates, a lot of them have salt concentrations very similar to seawater, and sometimes a little bit more than seawater. So they don't freeze unless the sea freezes, and if they keep away from the ice, they don't have that problem. But they still do change the chemicals in their cells to try and stop freezing. So they have more chemicals in their cells, which makes them more densely packed, which again we think affects how those cells can function, which slows down growth rates and slows down the development rates. So the physics of what you have to do to solve that problem of low temperature, of water molecules becoming sticky, because even if you can stop them freezing by making your cells and your body more salty, those water molecules still become sticky with each other, and they still become attracted to each other. Now every molecule in your body and in every animal's body has a glove of water, has a sheath of water over it. And when you change the physics between those water molecules, it changes all the other molecules. So if you make those water molecules more attractive to each other, it makes that glove of water much, much stiffer and much tighter, which means if you have an enzyme that has to open and close, or a protein that has to open and close, or move or change its shape to do its job, and thousands of proteins have to do that, then if you make the glove on the outside stiff, it makes that job a lot harder to do. Which again affects the growth rates, it affects the ability to develop. If you think of haemoglobin, we have haemoglobin in our bodies, and it carries oxygen from our lungs to our tissues. And the way it does that, it's like a clamshell. It opens up, grabs an oxygen molecule and moves around the body. Well, that just opening and closing of the clamshell, if you make that way stiffer, then that becomes a much harder job to supply oxygen to your tissues.
Yeah, yes, exactly. So what we're seeing when we think climate change, we can very quickly imagine the kind of loss of the ice that you mentioned earlier. 2 miles of ice going. That's in a kind of warm environment. That's an hour's walking to get to that. A lot longer in the Antarctic. But there are consequences on the biological change of the ecosystem change, on the nature that's there, is only just being kind of understood and discovered because, as you said, if there are just on the seafloor 20,000 species and more humpbacks and orca and other things at the top of the food chain, as it were, they're present and there's a whole lot of other stuff that's going on and changing as well at the same time as the climate change.
And I think if anybody says we know what's going to happen, they're just wrong.
Yeah.
Because it's almost impossible to predict the outcomes for the life on the planet. And I would argue, and I mean I guess you would expect me to argue, that the most unique life on the planet is in the Antarctic. So there are some classic examples. And I think if it's unique in a way that nothing else is unique, it's more important for biodiversity.
Yes. Yeah.
So every animal with a backbone, all the amphibians, all the reptiles, all the mammals like us, all the birds, all the fish have red blood cells. They have haemoglobin. Except for 16 species of fish in the Antarctic that don't. And they survive on the 2 to 3% of oxygen that is just dissolved in the circulating fluids that go around their bodies. Now that is...
So they haven't got this clamshell of haemoglobin transferring it and doing the work. They're surviving on tiny amounts of oxygen.
So we carry 98% of our oxygen in haemoglobin.
Yeah.
They survive on the other 2%.
Wow.
And they can do that because it's so cold, and the cold lowers their metabolic rates, that their requirement for oxygen is 25 to 30 times lower than fish around our coasts and in the tropics. So they can survive. It doesn't take a lot of warming before their metabolic rates go up because of the warming, and they can't supply enough oxygen to survive. So, and we lose unique physiology, unique biology. So another example, we have sea spiders in the Antarctic.
So show us your sea spider.
Before we get there, sea spiders in the UK, the biggest ones are about 1.5 centimetres across. The biggest ones in the tropic are less than a centimetre, so we're talking this sort of size. Yeah. So this is not a very big Antarctic sea spider. This is sort of mid-range. The biggest ones are 50, 60, 65 centimetres across. So 2 feet, So
Size. Yeah.
3 times the diameter of this.
So you're thinking the alien where it grabs you around on the face, isn't it?
Yeah, very much so. And 24% of the world's species of sea spiders live in the Antarctic. Wow. On 10% of the seabed. So they are 2.5 times more diverse down there than elsewhere. And there are lots of reasons for that.
Are they predatory?
They have a whole range of ways that they feed. This one chases limpets. It's an active predator. And it puts its proboscis, which is this protrusion here, this short protrusion here. It pushes that underneath the limpet shell and eats away until the limpet falls off and then eats the rest of the limpet. So they are active predators. Yeah. And we don't have the standard crabs and lobsters in the Antarctic. And some of these guys have evolved out to fill that gap. Now, anybody who's watching closely will realise this sea spider has 10 legs. Yeah. And we have both 10-legged and 12-legged sea spiders in the Antarctic, but 90% of them are 8-legged, like sea spiders everywhere else. And it's an example of their diversification in the Antarctic that we've got 10 and 12-legged species. We have giant species. The biggest ones are 5,000 times bigger than the biggest sea spiders in temperate locations like Europe in terms of their weight. And they're a great example of unique biodiversity. And if we lose these things, we lose not only interesting unique biodiversity, but we lose all of that biology that we might be able to exploit. So if you, as a trite example if you like, where do you go looking for low temperature enzymes so that we can make washing powders work at 10 degrees or 5 degrees? Well, animals that have evolved for 25 million years at low temperatures have got those enzymes.
They're pretty good at it, right?
Yeah,
okay.
they're already good.
So that's a kind of question that follows from the detail of the research on the biology of these unique species. Is well, are there kind of applications in kind of human life elsewhere? The answer's going to be yes.
So there are already some. And Antarctic biodiversity is the least understood, the least exploited biodiversity on the planet. And it's not quite untouched, but it's pretty much untouched. There are very few species that have been looked at for their biotech. However, we already have research that's using antifreeze to try and increase the amount of time that you can use to take organs from transplant donors to the hospital transplant sites,
right, to
extend that time, and it's being shown to be possible, and it's being used in some parts of the world now.
Wow.
So antifreeze from Antarctic fish.
Yes.
Antifreeze from Antarctic fish is also being used to make ice cream smoother. So you get the ice crystals to the right size in your ice cream, you then put the antifreeze in and it stops the ice crystals growing any further. We have frost-free tomatoes being grown around the world because of antifreeze from Antarctic fish. We have a range of cosmetic products that include materials from Antarctic species that have been grown in biotech. There are 5 or 6 products being used in research. So during the extraction of DNA, when you want to do analyses of relatedness of organisms, there are 2 enzymes used in that have come from polar species. Wow. So we're scratching at the edge, and there are countries spending a lot of money trying to find biotech. Malaysia and Japan and China are spending a lot of money on biotechnology research on Antarctic species.
Wow. Very interesting. So let's shift species. Our friend behind us here. So tell us a little bit about our albatross friend.
This is actually a model of an albatross chick. I gave lectures on television for the Royal Institution Christmas lectures 20 years ago or so, and this was a model made for those lectures. And it was actually made by a guy who worked on Jabba the Hutt for Star Wars as an animator.
Wow, nice. Right.
He made Jabba's tongue, and he made this albatross chick for us. And the albatross chick we use to show a range of things. So the nest that it sits on is a false nest, and we have some research projects in the Antarctic where we've replaced the nests that the parents have made with these fiberglass nests. And underneath the nest we have a weighing balance, so that when the parents then come and feed the chick, we can see exactly how much food they've given the chick just by the changing weight on the balance.
Remotely measured.
Remotely measured, and we have 50, 60 nests like this, so we can see how well a colony's doing just without going into the colony, just by the weight changes in the chicks. And then as the weight of the chick declines over time, you've got a measure of its metabolic rate. And then when the environment changes, so for instance, there are plenty of areas in the Antarctic that are now getting rain that didn't get rain before, and when chicks get wet, they lose a lot of heat. So you can then see the rate of change in the energy loss because of the change in the climate, and then you can relate that to how much change you need before the colony fails and the chicks die. So that sort of research is really important in telling us the impacts of changing climates on the biology and the biodiversity.
Yeah, yes, how amazing, isn't it? We've got kind of iconic animals down there, whales and albatrosses and penguins and other things which kind of capture the imagination. And you've seen the retreat of the frozen environment over time. That impact upon us and our understanding of that. Do you see a kind of continuing challenge of how we tell the stories of, as it were, bad news? I mean, it is as bad as it can be, as you've described it. And how do we talk about that? You've explained a lot that's fascinating, but how do we talk about that in a space that doesn't make people just more anxious and thereby less engaged with the need for change? I mean, there's public discussion, there's also policy. You've done a lot of public engagement and thought about this challenge of telling it how it is, but not so much that people switch off from that. There's a kind of double edge to that, isn't there?
There is. So going regularly and seeing massive change in the Antarctic and seeing ice disappearing and seeing rates of melt that I've never seen before. So we basically have a big stream running out of a glacier near the station that I can walk to and watch that wasn't there 5 years ago, 3 years ago. And I find that really wearing, and I find it really a weight and a burden to carry around with me. So that gets me down. And you're right, I give a lot of talks to schools, to natural history societies, to public bodies, and we talk about this. And I talk about what I do. And I say, well, okay, we do have a car in our family, but we only have one car. I cycle everywhere. And I change my life, and it's a cost. It is something that I have to take on, but I feel that as somebody who is aware of what the changes are like, that I have to do something to feel good about myself. Yeah. So I've cut down the amount of red meat I eat. It's almost out of my diet. I eat predominantly fish. I eat some chicken. I cycle everywhere. I've given up taking aeroplanes to conferences for my work now, which means I don't go to conferences in other continents. I go to them on Zoom or by some sort of media across the web. But that means I sometimes have to get up at 2 o'clock in the morning to attend a conference in Australia.
And you speak in the middle of the night.
And
I
speak in the middle of the night. Yeah, exactly. And that's a cost to me. It's a drag for me. But
there's you've described a moral responsibility almost there to say that once you know these things, there's a question, do we just carry on building up that knowledge base, or do we start ourselves to act in different kinds of ways? And you've described the answer to that is yes.
Yeah, and what I try to do is to say to people, look, you have to live your lives the way you feel is the right way to live your life. I find as an individual that knowing these things about climate, I could not live with myself if I did not do some things to try and help. And it might be throwing things up in the wind and watching them blow away, and it might be of no value whatsoever. But for me as an individual, to live with myself, knowing what we're doing to this planet and not taking the actions that I could, then I would just feel bad about myself. We lived in a bungalow for 15, 20 years, and we converted it a few years ago into a house. And I said, I want twice the insulation that you would normally put into any house. And now our heating bills are about $1,200 a year for a reasonable sized detached house, which is way lower than it should be, but that's because the insulation is really high. Yeah. And yes, it will take us probably 20 years to pay off the cost of the extra insulation. I can live with myself better, yes, exactly, because I know I'm having less of a footprint.
But that says a nice thing about saying these kinds of decisions shouldn't just be conditioned by the economics. They should be conditioned from a moral position, from a moral stance, that you think from what we know about the world that we have to live with ourselves.
So I think every individual has a set of criteria that they live by. We have a set of desires, a set of wants, and a set of constraints that we impose on ourselves. We decide whether we spend money on X, Y, Z, A, B, C, and we decide how we live. So I've decided I'm only going to have a mobile phone every 5 or 6 years when the previous one doesn't work, because I know that the rare earth metals in those mobile phones are one of the big problems that we have in society. I think we all have to live with ourselves. I think most of us don't look in the mirror and say, okay, what am I made of? What do I believe in? We will pay for things that we believe in. We'll give money to charities because we believe it's right to look after animals that are mistreated. We'll give money to charities because we think it's wrong that people who are living in parts of the world where there's no food don't have food. Will we put the same moral effort and our own resources into fighting what is probably in the medium term the biggest challenge this planet has? Irrespective of the wars that are around the planet, climate change, if we do nothing about it, will kill hundreds of millions or billions of people in the next 100 years. I know that if I do nothing and I take 5, 6, 7 flights a year around the planet to go on holidays, I personally will kill somebody in the next 100 years with my contribution to climate change compared to what I do now.
Yeah, and you and me, we've both got grandchildren, and so we're now kind of invested in the people we don't know and the world as a whole. But when we're invested in the people we know, that changes things as well.
And I also don't want to think that I've been if you like, a small custodian on the planet for a lifetime, and I've destroyed a lot of it for the future. I don't want to think that I'm killing off lots of animal species by what I do, and I don't want to think that I'm destroying biodiversity and that future generations will never see that. But also, I mean, okay, humans are not going to be here forever, and in 25 million years' time, there will be biodiversity on the planet. I don't want us to destroy that for 500,000 years.
Accelerate that change,
Yeah.
exactly. A few quick fire things at the end there. So something you're proud of in your kind of, what are you most proud of in your science side of things with the British Antarctic Survey? What would you say?
So there are 2 or 3 things that I'm really proud of. I really like the fact that I found the link between giant size and the amount of oxygen in the environment. So there's more oxygen in the ocean in the Antarctic, twice as much as the tropics, and the metabolic rates mean the animals use that oxygen a lot more slowly, which means you can make a lot more animal for the amount of oxygen that you got. And we found that link. I also like the piece of work that I talked about before, seeing how development rates of animals are not only slow at low temperatures, but they're slower than they should be for that low temperature, and a lot slower than they should be for that low temperature. And we now have research projects looking at the physics of cells at 0 degrees. For the first time ever, we've built a microscope where we can look inside cells of animals at 0 degrees and watch molecules moving around in those cells and watch processes going on in those cells, and we're finding some really astonishing things. It's coming at the end of my career, but it's some of the most exciting science that we've ever had.
That's how it should be.
It is.
Exactly. It should be like that. Vulnerabilities, being in a hole, getting out of a hole. Things don't always go well. They go down, they go up. You described a big hole that we're all in, the climate hole, and seeing that each time you go to the south, but something kind of personal. So papers rejected, you get grants rejected, that's the name of the game. It's never easy.
So I'm a scuba diver, and I scuba dive in the Antarctic, and I've got several hundred dives, maybe 800 dives in the Antarctic. I've dived when there's been solid ice on the surface, and the way we do that is we go out, we take a 5-foot chainsaw, we cut a hole in the ice with a 5-foot chainsaw, which takes about 3 or 4 hours. Then we dive through the hole, and everybody has a rope tying them back to the surface so you can come back to the hole. Twice I've been on dives in those times where you get to the end of the dive, you signal on the rope to say we're coming back, and we've pulled the rope in because the guy at the other end didn't tie it off. Now on the first dive, we were diving on quite a decent slope, so we could just turn around and come back on the slope at the same depth until we could see the hole. The second time we were on a flat seabed, and I pulled the rope in and thought, well, we're dead.
And you can't just look up and say, oh, there is the hole.
Well, no, because you're 150 metres or 200 metres away from the hole, and you just can't see it. So I thought we're dead, and the guy I was diving with was a very experienced Antarctic diver, and he signalled to me to go up to the surface, and I thought, well, there's no point going to the surface. We have a metre of ice up there. We aren't going through that, and even if the guys above us can see us, they can't break the ice and get us out in time. So I thought we're dead, and he insisted we went up. So we did go up, and then when we got close to the surface, I realised why. Because he knew that divers blow bubbles, and we followed the trail of bubbles under the ice back to the hole, and he saved my life.
Isn't that amazing?
He got us out of that hole.
Amazing. The next question is about your heroine or hero. Well, I guess that diver's one of your heroes, isn't it?
He's got to be.
Who would you point to?
Well, there are several in different parts of my life. Academically, I was taught by a guy called Simon Madrell, who not only one of the brightest people that I know, and he was a lecturer in zoology in Cambridge. But when I came back here to work, I built a small collaboration with him, and I would regularly go and talk to him about my science. Now, this is a guy who is one of the best scientists I've ever known, and every time I talked to him, he wanted to know about what I was doing, and wanted to know about the science I was doing, and wanted to understand it and help me understand it in ways.
Oh, that's nice.
We did work on fruit flies where we kept fruit flies in different oxygen levels, and when you lower the oxygen level with the fruit flies, they all get small. So we showed that the oxygen relationship with our animals in the Antarctic, you could do the same thing with fruit flies in a laboratory here. And he was also one of the most accomplished people I know. So he was the university shot put champion. He was his college squash rackets champion. He won prizes for his daffodils in the Isle of Man flower show. So he was a kind of polymath
Yeah.
in terms of his skill, and he
But
was one of my real heroes.
That's lovely. Doesn't that describe the kind of the context, the hinterland in which we live? You can do lots of things, and you can be interesting and excel in those, as well as be interested in other people, as you've described his interest.
And I think the biggest thing I learned from him was interest in other people and other things, and being curious, because his driving motivation, I think, throughout his whole life was he was curious. He was just interested in everything, and it was insatiable.
A book or cultural item or well, we mentioned discoveries, but something of your own that you feel strongly about. It's the discoveries that we've already discussed.
So it's trying to understand how temperature affects life on Earth. And it affects it in the hot side. I could probably have gone to the hot side and looked at how the hot side affects things. But for me, the cold side has the best questions on the planet. And these questions about why can some things live in some places and not others? What is it about the environment that stops them living there? Why don't we have crabs and lobsters in the Antarctic? And I think it's something to do with the amount of force a mussel can generate is affected by temperature. So that especially the power. So repeated movements you can't do at low temperature because you lose the power. And I think when you watch a crab squashing something, it does repeated squeezes, and you lose that ability at low temperature. They just can't do it. So I think temperature has limiting effects, and not just limiting effects, but it allows things to happen. So we did some work on predatory snails, and we wanted to look at whether they fed on the same things. Did they have feeding preferences? We brought 100 of these snails back. We put their food items on the bottom of the tank. We ran the experiment for 3 years. One of those snails ate nothing for 3 years. 3 of them ate 1 meal in 3 years, and of those 3, 2 reproduced in the last half of the experiment, and they all moved around the tank at the same speed as all the other snails. What we realised was, at low temperature, your energy use is so low that if you just don't like what's going on, you can wait.
Just wait for 3 years before you have another meal.
And if you do that in the tropics, you're dead in 3 months because you just run out of energy. So the low temperature allows biology to happen that you can't have anywhere else.
And our sense of understanding of time changes as well.
Absolutely.
Isn't that interesting? A book to recommend. What would you like to recommend?
So I think Jared Diamond's Why Societies Collapse changed my view of human society. So the ideas in that book and the data in that book showing that regularly throughout history, human societies have exploited the environment to the point whereby they destroy it and it collapses. Easter Island is a great example. There were several tribes living on Easter Island. They were making canoes out of trees. There must have been a time when there were maybe 100 trees left on the island, and those tribes looked at them and must have realised that if they cut the trees down, their lifestyle of going out and fishing in canoes was no longer sustainable. But the immediate imperative of getting more resources than the next tribe and having more in their pockets at the time overrode that, well, okay, we're not going to be here in 100 years' time if we cut those trees down.
So it's the psychology of change again, isn't it?
It is the psychology. And there are many examples of human societies just continuing to exploit when they know that they've gone past the point whereby it's sustainable. And I just hope...
Maybe we run out of ideas at some point.
Yeah.
Or we run out of energy, or
Maybe
those internal pressures. One top action for people. What would you like to recommend?
So I would say, look at what you do, and look at one thing that you can change to help the planet, and do that once every 6 months or once every year, and do it increment by increment. But take stock. Stop and take a cold look in the mirror and think about, what am I doing? What can I do to help things and to make things less extreme in 10 years' time and 20 years' time and 30 years' time. Don't change your life overnight. Do it bit by bit, but stop and think.
I love that idea. Do one thing. Don't try to be too perfect, because we can't live up to that aspiration.
Absolutely.
But we can do one thing, can't we?
Yeah.
Lloyd Peck, thank you very much indeed. It's been a super chat to be in your office at the British Antarctic Survey, to have this insight into life in the south, in the coldest part of the world. Pleasure to have you on. Thanks very much.
It's been great, Jules. Thanks for having me.